Yeah, to start with CARLsim, a little bit background. There was a very important paper which describes a neuromodularity system. And this effectively was the initiator to do a CARLsim 6 development, which is essentially the implementation of those 4 neuromodulators that implement this neuromodularity system. We were able to write a paper and presented it in WCCI, and there were a couple of universities involved. It was a big team effort, and to introduce CARLsim a little bit, perhaps we should take a look what it is. It is a fast and efficient simulator for spiking neural networks, and especially it scales over multiple GPUs. It is used for biological detailed large-scale SNNs, and it runs on off-the-shelf robotics hardware and can drive autonomous robots. To have a little bit technical background, it is implemented in C++ and CUDA. Most important, it is open source and available in GitHub, and the project is hosted by UCE CARL. And it can be downloaded, and there is a community. It gets some attention, and to have a little overview over the technical features, CARLsim 6 mainly addresses those in the kind of system maintenance. As for instance, we had introduced a CMake build system to support those abundant mass of hardware and systems. We are able to create DLLs, Visual Studio, and most important, CUDA 11. And also there will be binaries, open source community, Docker support, and some other stuff like the Python offline analysis toolbox. On the right side, you see the feature list, and here are the more technical maintenance features. And as you see here, CARLsim outperforms all the other possibilities that are currently around, and so it's kind of best of choice to use. And to have a little more to how CARLsim works and how the basics are, I would like to hand over to Jinwei. And Jinwei, could you share your screen?
Yeah, here I'm going to introduce some the basic concepts in CARLsim to help other people to know more about it. And then later, after the basic introduction of the CARLsim, the key concepts, we are going to have some introduction about some features of CARLsim 6. So the workflow of a typical CARLsim simulation is organized into 3 distinct and consecutive states: the configuration state, then we are going to do a setup, and do a run state. So in the configuration state, we are just basically tell the CARLsim what kind of neuron groups we are going to have and how they are connected. And this is just like a setup. This is just tell the CARLsim the configuration of our networks. And in the setup stage, we are going to assign the memory space and create the neuron groups with create the neural groups and assign them on the different devices. So this is for the setup. And during the run stage, we are going to tell CARLsim like how long we are going to run the simulation. And yeah, basically in the run state, we are going to like simulate the activity of the spiking neural network. Yeah, we can go to the next slide. And for the neurons, like basically we have like 4 types of neural models and a 4-parameter HCAVH, 9-parameter one, and multi-compartment neural and LRF neural models. And to notice that like when we create the neurons, they are created in groups. For example, like we're going to, we have like 2 commands here. The first command is going to create a group of, for example, 100 HCAVH neurons. And once it's created, we can also set the parameters. Like for example, here, the default one is that we choose like a 4-parameter HCAVH neuron. And so we are going to assign, we're going to like set up the parameter for this neural model. And next slide. Yeah, so once 2 neuron groups are created, we can use the synaptic connection function to build a connection between them. So for example, like we have some like 4 types of predefined connection. For example, all-to-all, random, one-to-one, Gaussian connectivity. And this is like a basic introduction of our connection function. And we can see like, for example, the first 2 parameters are the group ID, which is the result that we get from the create group function. And then we also define the connection type, the weight, and also connection probability, and some other, more advanced like hyperparameters. So basically, like we have already introduced, like we have the neurons. Neurons are created in groups, and once the groups are created, we are going to build a connection between them. And also, once the connection is built, like we are going to build some create some synapses between the neurons. And can we go to the next slide? Yeah, and also for the synapse between the neurons, we also allow them to give them the synaptic plasticity. For now, like we support some, for example, STP, STDP homeostasis, and we are going to have some more like synaptic plasticity modes introduced as some new features in CARLsim 6. So yeah, we can go to next slide.
Take over the presentation. So here we list some of the new features that are implemented in CARLsim 6. So that includes some neuromodulated STDP and like some other enhancements of previous implementations of STDP and STP. We'll talk a little bit more about this later. And as you can see here, CARLsim is the only one simulator that has like all these features implemented. So it provides a lot of flexibilities and also like biological, I guess, plausibility when we simulate spiking neural networks. And
Kexin, I think we hear you a little bit too shallow in the recording. Perhaps you can switch the microphone. Yeah.
Watch out for the cords.
Over here. Okay.
Yeah, that's much better. Great.
Right. Let's see. So we talked about like some, I guess, feature enhancements. I guess we can go, yeah, this slide. So the new features, we can kind of like look at them in 3 groups. The first one being structural features. So previously, STDP is kind of specified on group level. And in the new, I guess, latest release, we allow, CARLsim 6 now allows the users to specify STDP curves per connection and also STP. And let's see. And we also added neuromodulated, neuromodulations on those like synaptic learning rules. We can go to the next slide. So as Jinwei described earlier, we define neurons in groups and then also define connections between the groups with a, I guess, specific, I guess, C++ class that we define as connection group. So for the neuron groups, CARLsim 6 supports different types of neuron models and also could be implemented in conductance-based and, current-based models. And also, as you can see here, CARLsim 6 now allows the users to specify STDP curves per connection and STP. And we also added neuromodulations on those like synaptic learning rules. We can go to the next slide. So as Jinwei described earlier, we define neurons in groups and then also define connections between the groups with a, I guess, specific, I guess, C++ class that we define as connection group. So for the neuron groups, CARLsim 6 supports different types of neuron models and also could be implemented in conductance-based and, current-based
So here, let's see. Yeah, I guess for like the orange text, we kind of listed a whole bunch of new features added to CARLsim 6. I guess we can go to the next slide. So here's an illustration of how the new STDP configuration would work. So we can look at the code on the bottom right corner. So here we have two connections. They both, we have two neuron groups, an input group and an output group. The two connections, they both go into the output groups. So in the current, the new implementation, we could specify different STDP learning curves for these two connections with different parameter settings. And so let's see. So with these like additional parameters, our network is able to, I guess, approximate any function like more closely, and that also like adds biological plausibility to the SNN model. And CARLsim also supports eligibility trace-based STDP with different neuromodulators. I think in previous versions, we only support dopamine modulated STDP. And now we have like support for all different, I guess, all 4 types of neuromodulators as listed here. And in the figure, I think it shows the analysis done with the offline analysis toolbox that comes with CARLsim. So as we can see here, the bottom figure, the red curve, shows the dopamine level in the target group. And as the dopamine level kind of decays, we can see that the synaptic weights kind of also decays. And as we kind of accumulate the dopamine level, the weights also gets updated. And on the right side, we can see that each connection, we can specify different types of neuromodulators for the STDP connection, STDP learning rule. I think that's pretty cool.
Mm-hmm.
Okay.
And here we're showing some long-term potentiation and long-term depression of STDP, this kind of curves. So as we can see on the left figure, if we look at the green curve, it basically shows a more like balanced, I guess, balanced level of LTP and LTD. So in CARLsim 6, a new feature is that we could use an arbitrary pair of neuromodulators to kind of modulate the relative strength of LTP and LTD. And that would allow for learning and unlearning to kind of happen more dynamically, as shown on the right figure. And we can go to next. Yeah, I guess we can go to the next one.
Yeah.
So here, this is a project I guess done by the George Mason Group. It's a pretty amazing effort. They had a large, very realistic spiking neural network model of the CA3. So they were able to simulate many different types of neurons and also like have very specific STP parameters assigned for each intergroup connections. So as we can see from the figures, they're able to observe different like I guess activity and like different dynamics of different types of cells. And so I think they also contributed a lot to the analysis toolbox. They allow them to make the analysis of like these different, I guess, like firing phase histogram and like power spectrum of the cell activity. So you can look into their paper if you want to learn more about like how they implemented this model.
Okay. Yeah. Thank you, Kexin. Yeah, some more features. I only want to briefly show it is the receptors. We can model synergistic and antagonistic receptors. That means they can work together or against another, and they can be configured so that two neuromodulators define their excitability, and therefore it is, for instance, possible to implement thalamatic neurons that control the information flow, the spike flow, depending on the current state of the neuromodulators. And another application here is a work that's from 2013, which describes the prefrontal cortex, which was investigated for discrete values, and with CARLsim 6 it is now possible to leave those neuromodulator values on the complete area on the plane, and therefore you can also use this model for the areas between and investigate with what happens exactly in the state of the neuromodulators, and when those observed memory impairments actually occurs. So to conclude the functionality of CARLsim 6, I think it's worth to mention it's positioned to span a new ecosystem, and it shall motivate new projects. Essentially here it is a matured core library with a powerful support system, for instance, this OAT monitoring. So also that it benefits from the latest hardware like the NVIDIA supercomputer, and therefore this maintenance effort. And especially this hippocampus project, the CA3 project, has proven again that CARLsim 6, CARLsim is biorealistic. And this means that you can, together with this neuromodulary system, develop circuit models for the various brain areas. And we want to have this CARLsim 6 to be used for neuromorphic computing, and especially to neurobiological inspired cognitive machine. And so this is the whole thing from the CARLsim 6 feature perspective. Are there questions so far before we go to further what's is in the pipeline and the future brings with CARLsim?
Could you explain, I think it was like on slide 14 or somewhere, just again, protein kinase A and phospholipase C, the push-pull rule? Like what's going on there? I think that was Kexin, actually. So sorry.
Lars will probably have more context on that.
The acoustic was a little bit disturbed. Yeah. This.
Yeah. Okay.
Yeah, this was a question, this push-pull rule, yeah?
Yes.
Okay, yeah. So it has been observed that there is this protein kinase A and phosphorylase C, and this actually alters the STTP curves. This means that the learning can be modulated by neuromodulators, and there is a nice backup slide here, which shows the scenario here. You can implement certain aspects for adaptive learning, and for instance, you can enable rewiring by providing certain levels of neuromodulation levels. Yeah? For instance, here we have the norepinephrine at 1 and acetylcholine at 1, then it's equilibrium, and it's a standard STTP curve. However, if you set acetylcholine to 0, you have another STTP curve that is also known and was observed, but it was so far statically configured. When you go to the CARLsim tutorials, it is explained there as a sample. And that means before CARLsim 6, you had to model your model in a static way and decide, okay, which STTP curve might be the correct one. And yeah, it could have worked or could work for a certain aspect. However, if you want to implement an adaptive behavior, then it's probably a little bit difficult.
So these are changing dynamically based on the neuromodulator level?
Exactly.
Is the neuromodulator level a scalar or is it a neuron? Where's that coming from?
So this is molarity of the group, which is captured in the group.
Okay.
Yeah. If I may. When we go to back to the configuration slide, almost there. Yeah. You have this energetic neurons which project to a postsynaptic neuron group, and there the level of dopamine and the other 4 neuromodulators are captured.
And this is also in coincides with the excitatory eligibility trace type of neuromodulated STDP, or is that
Right, exactly.
are those? I guess those are configured separately, though, right?
Yeah, exactly. You can decide either or the other. Yeah, you can configure standard STTP or neuromodulated or eligibility traced. It was okay. I go back. Sorry for this flipping here. You can configure this on connection on the connection group level. Yeah.
Nice. Here, can you go to slide, I
Okay.
think it's 21, where you showed the Avery work?
Yes.
That one.
Sorry. Yeah.
Yeah. So what Mike Avery did to show cholinergic effect on neurons was he dynamically changed, I think it was the B parameter of the Izakevich neuron, which I don't think ever got implemented. But that one thing he had read and they had observed was that when you get cholinergic activity, that you get bursting behavior. You go from tonic spiking to bursting. And so he put that, I think, in a very separate branch, which also might be something we want to think about in the future of having, since we have all these dynamics, to have dynamics on the A, B, C, D parameters for the simple model, and then I forget what other parameters. But Izakevich defines some of those parameters as having specific effects on the dynamics of the neuron. So it might be something we want to think about in the future that gives further flexibility to people. I've had other people ask about how to do that outside our group. So
When would you choose the 9 parameter versus 4 parameter?
the 9-parameter, 4-parameter captures a whole bunch of neural activity. But then to get some other neuron types, which are rarely used in modeling, but some people do, you need 9 parameters. And I know the George Mason group has used the 9-parameter model. And so Izakevich at some point realized that to match some other neuron types, he had to have expanded the 9 parameters.
I have a question. I have actually 2 general questions. Do you happen to have any sample of a neuron group, actual neuron groups that are in the brain, for example, like CA3 or something?
Yeah, exactly.
Yeah.
I think the best example here is this work from George Mason, because they used this hippocampal drome database where those parameters exactly have been captured, documented, and Jeffrey Kopsik exactly has used this 9-parameter model to implement actual eight different types, 1 principal and 7 interneurons. Yeah.
Cool. And my other question is, have you ever done any study on how memory intensive is CARLsim, or like the system requirements that you need to have in order for it to be real time, or these kinds of have you ever done these kinds of studies to?
So you're asking about a memory model over time? Is that what you're asking?
I'm asking, have you ever done any kind of a study that shows how memory intensive is in terms of computing? I mean, in terms of computing, how much memory it needs, how much of a GPU, or yeah.
Oh,
Okay, you mean
yeah.
the technical requirement, the consumption and so on. Yeah. Okay. We have done with CARLsim 6. We have proved that the performance is equal as the predecessor versions. This was the slide in the beginning here. So we didn't have an objective with CARLsim 6 to do any performance improvement, yeah, but by the usage of CMake, for instance, we benefit from the latest hardware, which means, for instance, this retail graphics card, RTX 3090, has 24 gigabytes of memory, which former only Tesla cards had. So yeah, and I think you can build from experience models with millions of neurons, but it strongly depends on how the synaptic connection is structured, and because this is actually memory bottleneck, let's put it in this way. Yeah.
Mm-hmm.
And it's really depending on the model. But for instance, George Mason were able to model a biolistical full-scale CA3 of a mouse with CARLsim.
Oh, is it real time or like?
No.
No. Okay. I just wanted to get an idea of how. Yeah. Thanks. Yeah.
For real time, kind of get an estimate. If you look at Michael Baylor's paper that was in Neural Networks a few years back, there was no learning when he did it, but he had a very large scale neural net. I forget how big it was, but that was running in real time and it was controlling a robot through Wi-Fi. So that'll give you an idea how big a network we can run.
Cool. Thanks. Yeah, I was just wondering if our robots have the capacity to run CARLsim, for example, HSR, because I think it has a GPU, but I don't think it can run
It does
CARLsim.
depend on the GPU. I don't think the GPU or computer on the HSR physically is very strong.
Yeah.
Whenever we had to do real-time work, actually be outside the lab when we went to RoboCup, we had to strap a laptop. Well, you did this too. You know,
Yeah.
you strap a laptop to the back of it. So if you have a laptop that's got a good GPU,
Yeah.
and you use the Ethernet connection, you actually can run a CARLsim or other simulation that's pretty large scale.
Cool.
Yeah, and then you're just at the well, you know this better than I do. You know, then the issue is the battery length of your laptop more than the HSR, because that was what was always running out for both you and then we went to RoboCup.
Yeah. I guess all kinds of industries are dependent on batteries and yeah.
The bane of robotics and other things. Yeah.
Is this the Baylor paper that you're talking about?
Okay.
Yes, that is.
40,000.
How many connections? 40,000 connections. 40,000 neurons.
With 1.7, I think.
1.7 million connections.
Yeah.
Okay.
But we did have learning disabled. That would slow things down.
Okay. So if there are no more, or are there other questions? Otherwise, I would like to show another application which is currently in the pipeline, which is called axonal plasticity. Okay. I switch. Okay. Yeah, this axonal plasticity is a very new rule. It encodes cost in synaptic delays, and until now, the main learning and effort here was spent on targeting the weights, and this new perspective or these new findings have shown that especially in the CA1 of the hippocampus, this axonal plasticity takes place to encode environmental cost like traversal cost. And those delays are changed according to learning rules like e-propagation or delay-dependent STDP. And there is also a biological plausibility as the observed growth of the myelin sheath that results in faster spike transmission. And I think we have seen some applications already in the first lab meetings. And also we had a first feasibility study in Q2 for CARLsim. And there are there's some good progress. And meanwhile, we can have we have CARLsim UI, and it can show the actual, it visualizes the myelin sheath thickness, which is refreshed every 500 milliseconds. And the actual updates are determined by a first version of a e-propagation. I can show you a little bit more vivid, hopefully, yeah. And as you see here is CARLsim GUI, its first version. And you see here this 4x4 matrix. And I stop this just a moment. yeah, now you have already seen this waveform propagation, and when 500 milliseconds are reached, here the myelin sheath is thickened. Yeah, so this enables a visual feedback, and compared to the stuff we have already implemented a while ago, here you see this the analysis of the offline analysis tool and some specific MATLAB scripting. Yeah, and here it turned out that here's the algorithm laid out find wavefront path. It returns the path and the eligibility. Here is the calculation is done for the updates, and the critical part here is the update delays. And the tricky part here is, which is kind of real challenging, as Jinwei explained, usually there is a strict step and workflow. You configure, then you set up, and then you run. And when you run, we already discussed about real-time performance. So there is a lot of optimization being done from the, let's say, logical model down to the physical model. And especially the delays are being dissolved. Yeah. So when you have a connection, usually you have a weight, yeah, and you can manipulate this weight. And when the next step runs, then this weight is expressed. However, this is a delay. The delays go to this timetables structures, and so the solution is to be able to implement axonal plasticity. I had to revise those data structures at runtime. Yeah, and the current status here is the SNL model now has forward and backwards connections. For the first test, it was only one direction, but when you consider a maze, of course, you can go from any point to every other. And this spike wavefront propagation is been tested, and the path extraction with this figure 1 model of figure 1. And the update delays, there is still some progress. Yeah. Also, when we are talking about development with CARLsim, this is a fantastic showcase how some of the CARLsim 6 features do come into play. Here is the unit, small unit test for this figure 1. You see here this maze of the paper, and here you see how you have two groups with different conductances. Especially the pyramidal has no conductances, but the interneurons have conductances, especially configured. Yeah, and yeah, here's the actual call in the code. And when you start CARLsim, it looks like we all know this. It is started. You have the terminal output, which displays the networks, and this specific test case implemented some text output. Yeah. Like you see here, the connection matrix, then how the spike wave is propagating. It's the same spike wave we have seen in CARLsim GUI before. And finally here, the path is being found. Yeah. So while CARLsim OIT enables great detail analysis, quantitative detail analysis, and unit testing is mandatory. It gave, so this approach so far, it gave a great control for well-defined scenarios. And however, when you think about more complex model like field applications, like they are necessary in field application, some kind of tool would be great to help to visualize the structure of the SNN and its dynamics. And yeah, that's the reason why this CARLsim GUI is one of the next major feature. And it is a graphical editor for spiking neural networks. It integrates OIT monitors and spike generators. And it yeah, you can analyze interactively on the structure and the dynamics. However, most important are the plugins. You can have specific plugins, for instance, I show you a small sample, the VTE, the external plasticity, how this plugins behaves. And yeah, vielleicht, where does this CARLsim GUI originate from? There is another tool stack. It was called Spike Stream some years ago, and there is some, yeah, this was some kind of no further development in the Spike Stream, and I implemented some nice features there, including some migration of the latest Qt versions of CMake, and another technical background which is very nice. It's that the spiking neural network is persistent in an SQL database. It is fast, and yeah, it has this API for plugins. And what does a plugin means? For instance, for our sample model, you can, with a few lines of code, you can build a network plugin where you can add a network by a press of a button. There you have pre-configured values, and the traversal cost are behind this button. And it results then in such a nice yeah, network, which can be shown. I say how it behaves. So when you start this GUI, it shows pretty much a small splash screen. Then the first step is you choose a network from your database. Then you have the database, the network loaded from the database. You can manipulate, you can browse in this tri-dimensional aspect, and you can, for instance, also mask out those areas which are not of your current concern, because we only want to see this spike wave propagation in this sample. And yeah, this experiment shows that the neuron with the ID 0, which is in the back corner, was excited, and so you have seen this wave propagation. Okay, so I think this gave a small impression, and yeah, this experiment, also this experiment thing is a plugin again. It provides a simple user interface. You have parameters, and you can start this experiment with a simple button. And it visualizes this, as we've seen in the beginning, the actional delays and the changes online. Also, I think worth to mention is that this CARLsim GUI allows this OIT monitors to be used online. It can be configured as a model parameter, and then after you loaded this network, you have here the spiking monitor, and I let the experiment run a little bit to have some activity in the network, go back to the monitor, stop the monitor, see a printout, and then you have a HTML report how when those monitors have fired. You have some statistics, and this is all during your simulation time. So it's not, you can do it on the fly and get a more intuitional feeling how your model behaves. Yeah. So it is to be seen as supplemental extension. It does not replace an OIT, but it gives you a great insight of your model. Yeah. And yeah, and also of course to come conclusion, this is a new CARLsim GUI feature. It, especially when showing an SNN expert to non-IE expert, it might have a higher impact because they can imagine a little bit better how a brain works, it fires, and yeah, an OIT report is only a very condensed form. Yeah. And yeah, as mentioned, it is extensible by plugins. Most important, CARLsim can be used without programming. So this means those plugins can be built beforehand, like a toolbox for a hippocampus, and then you can plug in or connect a hippocampus via CA1, 2, 3, and so on, or the computer science department or support will do some plugins, and the actual study can be done without programming. Yeah. Yeah. And also, as the SNN is stored in the SQL database, this gives a bunch of nice manipulations. You can, for instance, change the weight for a single synapse, or you can run SQL queries to analyze your model, and it is reproducible. So when you load this model, it is always the same model, and also if the original connections were random connected. Yeah.
Let me ask
Yeah,
about
and
the
there are
SQL, Lars. So you're saying that we could save a whole network or checkpoint a network in an SQL database that's
right, exactly.
and load it without anything else, just from the SQL database.
Right, exactly.
So
Yeah.
we can make a library of SQL spiky neural nets of different projects.
Exactly. Yeah, you can. Yeah, exactly. Yeah, you can have actually a pre-configured when you have a real big network. You can provide dedicated network. You can have one database holding only one network with archived versions and so on and so on. You can clone it. You have a whole bunch of database operations. It's a MySQL database, so it's open source, of course, and you can provide a database with some samples, as we have seen in the video clips here. And of course, you have this other library, the plugins, where you can produce whole networks or network groups, also with a toolbox, from a toolbox. Yeah. Yeah. Mm-hmm. Other questions?
just want to say, Lars, this is fantastic. This is a major software engineering step for CARLsim. Thank you for the effort. I think,
Thank you.
this is really changing and probably pivoting in terms of making this more usable and reproducible. So thank you. That's I think and secondly, I think the GUI that you provided would be great as a teaching tool. I think for introducing SNNs to newer kind of newbies in some sense, because you can take smaller networks and show them how the rules work, and so that's also a very nice addition. So, yeah.
Thank you.